In the previous video, we finished deriving the normal equations and then the loss minimizing theta hat by solving normal equations for theta hat. I want to briefly return to this equation here and talk a little bit about its structure. So we can depict this matrix equation in terms of rectangles illustrating each of the matrices. When I work with matrices, I often find it helpful to draw boxes representing the shape of those matrices to reason about the dimensions and the underlying operations. So here I've drawn our X matrix in blue. Notice this is the X matrix is a D plus one, or sorry, it's an N row matrix with D plus one columns. And again, I've put the ones here to indicate the very first column is the all ones vector. So if we take X transpose X, it looks like these two blue rectangles. Here, X transpose, I've transposed this blue matrix. And then on the right, I have my X transpose Y. So again, my blue transpose matrix. And then my column vector Y corresponding to the response variables in my data. So the things I'm trying to predict. Now, in most settings, N is going to be much larger than D. So these are what we'd call tall, skinny matrices. So X would be very tall and very thin on the skinny. And likewise, the Y vector is going to be, well, of course, one column, but it's going to be many, many rows. And especially when you think of big data, we often think of N being many, many rows of data. In this operation, you'll also notice that we're taking the inverse of this product of matrices on the left. And so one thing you might wonder is, what's the size of the thing I'm inverting? So inverting matrices can be expensive. It's cubic time, or roughly cubic time. And so what is the cost of actually doing this matrix inversion? It's important to actually work through the matrix multiplications first. So instant replay. So we take our matrices here, the two X transpose X and the X transpose Y, and we can multiply these matrices through. And we get these gray boxes corresponding to the results of these products. It's important to note that once we've done these matrix multiplies, we're left with things that are on the order of D. So D plus 1 by D plus 1 and D plus 1 by 1. So these are much smaller matrices on the order of number of columns in our table and not the number of rows. And so then we have to invert this D by, or order D by D matrix instead of a matrix it's the order of N. Now, actually, in practice, it's often better not to directly invert these matrices, but recognize that we're originally trying to solve a system of linear equations. So the normal equation itself writes down a system of linear equations where you can rewrite this X transpose X as this, again, D plus 1 by T plus 1, or order D by D matrix, A, times theta, which is the thing we'd like to solve, or solve for. And then on the right, this X transpose Y is, again, a D plus 1 by 1 vector. We'll call this B. So this is really A times theta equals B. So this is the definition of a system of linear equations. And we can leverage this representation to use more efficient linear solvers to solve for the optimal theta. So in the next video sequence, we'll walk through the use of Python to implement the solution to this equation.